In this unit, we are going to be studying chemical equilibrium. In chemical equilibrium, we have reversible reactions. In a reversible reaction, the reactants can form products and the products can form reactants. If the rate of the forward reaction equals to the rate of the reverse reaction, then we have a situation called chemical equilibrium. And we can apply it to these ants here going across the screen. So they travel to a pile, they pick up a rock, and then they dump it at their own pile. And then they return to get another rock. Because the ants are walking at the same speed, the rock piles never increase or decrease. Instead, they remain the same. And that's true for a chemical equilibrium reaction. The amount of products and the amount of reactants, once you get to equilibrium, they don't change. Equilibrium is the extent of a reaction, or how the reaction proceeds. And in stoichiometry, when we look at how many grams and how many moles we have, we talk about the theoretical yields. And there are many reasons why the actual yields can be lower. Some of it has to do with poor lab technique or poor measurement. But there is another critical reason why the yield is less, and that is because some reactions have a reversibility, so the products can form reactants, and in this case that will affect that actual yield. There is a competition between, because the products form reactants, then it's actually going backwards and you're producing less than you might otherwise calculate with math. In chemical equilibrium, as I said previously, the rate of the forward reaction proceeds at the same rate of the reverse reaction. And it's dynamic. So just like my ants kept walking back and forth, it's the same thing with a chemical reaction. You are continually having the reactants form products and the products form reactants. And it is related to rates. I can write a rate of my forward reaction and a rate of my reverse reaction. Remember, with rates, they only have the reactants in it. So I can do the rate of my forward, and I would have these reactants. And I could write a rate law for my reverse reaction. And we touched on chemical equilibrium just a little bit at the end of our rate laws unit. But we're going to come back to this concept of the rates of the forward and the rate of the reverse, those rates being the same. One thing that you can tell you're at equilibrium is because in the reaction vessel you will have some of every species. So as far as this chemical equation goes, I will have some of A2, some of B, some of AB, and some of A. So you should see a little bit of each one in your reaction vessel. So just like our ants, their rock piles don't ever increase or decrease, even though they're working all the time. The same thing happens in a chemical reaction. Once equilibrium has been reached, the concentration of the reaction mixture does not change with time. So even though products are continually forming, when I go this way, I am also taking my products and forming reactants, so going that way. The opposite of a reversible reaction is a complete reaction. So in complete or completion reactions, the reactants proceed from reactants to products, and there's really no way for the products to form reactants, for it to go reverse. And that is because the disorder, or the entropy, is so high that you're just not going to form those reactants again. A good example of a completion reaction is a combustion reaction. So in this case here, I am burning some sort of fuel that has carbon in it. There's a fire right there, so imagine wood burning. And there's no way to reverse this reaction. So once I form my CO2 and my water vapor, I'm also going to have some ash. There's no way that all that can come back together and form the log again. So this is known as a completion reaction because there's no way to reverse it. Looking at reversible reactions, there are several listed on this video. So this first one is a physical reaction where water vapor is being formed from liquid water, and just with the collisions on the surface, evaporation can take place, and I can have the liquid molecules break their hydrogen bonding just because their collisions are efficient and they're going fast enough and colliding with enough force that the water that's a liquid can form a vapor. And then if you have a closed container, the water vapor can fall back into the water and hydrogen bond to its neighbor. If this happens at the same rate of evaporation as condensation, then we say that this is a dynamic equilibrium. It's not that you'll have equal amounts of water and water vapor, but the rate of the water becoming water vapor is equal to the rate of the water vapor becoming water. And then another example right here is my N2O4 forming NO2, and this is also reversible reaction. And you can tell this one there's a color change. So I just have the one molecule and it decomposes and forms two NO2 molecules, which happen to have a reddish color. And then those molecules can combine with each other and form the colorless N2O4. And if it's done at the same rate, products forming reactants as reactants forming products, then I say that I'm at dynamic equilibrium. Here's another picture of that N2O4 and the 2NO2 forming. We start off with N2O4 initially, and then it reacts and forms 2NO2, and then I achieve a dynamic equilibrium between the colorless and the brownish red color. Here's a diagram that shows that equilibrium is being achieved. So initially I'm starting off with my N2O4 and I have none of my NO2. But as the reaction proceeds, you can see that the reactants start to disappear and the products start appearing. And eventually we get to some situation where things level out, so the concentrations don't change. When the concentrations don't change, then that we say that is at equilibrium. So as soon as you see those lines level out, that is the point of equilibrium. So right here. And you can see that the reactions will still occur, reactants forming products, products forming reactants, but because it occurs at the same rate, to our eyes it looks like things have gone still, that nothing is happening. And that's because the concentrations stay the same. Here's another picture. This one is graphing the rate, and you can see that the rate is equal. So the rate of the forward reaction, there's those rate laws, and the rate of the reverse reaction, they end up the same, and there's my equilibrium. So I can draw that on my diagram, and that's because the rate is the same. So using a collision model, as the amount of NO2 builds up, there is a chance that two NO2 molecules will collide, and when that happens, you will go from a product to a reactant. And then at the beginning of the reaction, there's no NO2 to have collisions, so that reverse reaction doesn't occur, but only the forward reaction. And as soon as you get enough product formation, then the reverse reaction can occur. Now, it doesn't matter where you start. So whatever your starting materials, you will eventually achieve equilibrium, where you have the rate of the product formation is equal to the rate of the reverse reaction, and the ratio will be the same of products to reactants. So in this first picture, I start with just NO2, and then my reaction proceeds. Notice we always end up with N2O4, more of it than the NO2. And then in the middle picture, I start with just N2O4. And then the last picture, I start with a little bit of each. It doesn't matter where your starting point is, but when you get to equilibrium, the ratio of products to reactants, that number will be the same. Here's a picture that shows a whole bunch of different concentrations to start off with, but we see that this ratio of products to reactants, that we get a number that is the same, and it's a constant, and this is called the equilibrium constant. The equilibrium constant for a particular reaction at the same temperature will always be the same. And the equilibrium constant is given a capital K, and it's also given another letter like a subscript. If this K has a Eq attached to it, that's just a general equilibrium constant. I can take the rate laws and I can write what's called an equilibrium constant expression, or it's a formula that helps you figure out concentrations when you're at equilibrium. And this is how you derive the equation. I don't think that you really need to pay too much attention to this, but you should know the general formula. And that is that you have the concentration of the products. Remember, the little brackets means molarity, which is moles per liter. Products go on top and the reactants go on the denominator. So going through how this reaction is derived, if I take the rate of the forward reaction, for this particular reaction, I can write it. I can take the rate of the reverse reaction. Now my product is the concentration, so that's in my rate law. At a certain temperature, the rate of the forward reaction is equal to the rate of the reverse, and so I can put those parts of the equation on the same side, and I get the one that you need to be worried about. So KEQ, which is a general equilibrium constant of concentration of the products divided by the concentration of the reactants. So it's always products divided by reactants. KEQ, this equilibrium constant, is dependent on temperature. If you change the temperature, then your equilibrium constant will change. Catalysts do not affect the equilibrium. They just help you get to equilibrium faster. So that's a little bit different. When we were talking about rates, the catalyst does affect the rate. It helps it go faster. But as far as equilibrium constant expressions, it doesn't change our equilibrium constant. And one thing that you should know is that the equilibrium constant has no units, so it's just a number. Another name for equilibrium constant expression is the law of mass action. As far as equilibrium constant expressions go, we do use the balanced chemical reaction to help us to write it. Again, you're going to have products on top, reactants on the bottom, and whatever the coefficients are in front of each of the species, they will become the exponents. Now, you only include gases in your equilibrium constant expressions, and also anything that's aqueous, anything that's dissolved in a liquid. Never include solids and never include liquids. As I said before, KEQ is the general equilibrium constant. You will see on the AP test these two values, Kc and Kp. So Kc just means the equilibrium constant for molarity. This again refers to aqueous or gaseous concentrations. And another one you'll see is if there's only gases. If there's only gases, then we use pressure values, and so we'll use what's known as a Kp. Toward the end of the unit, we are going to apply equilibrium constant expressions to solids that are dissolved and have achieved that equilibrium of dissolving versus re-solidifying. And so we will see at the end of this unit a KSP. Let's write an equilibrium constant expression for this reaction. So it's just a general reaction. A plus B yields 2C. And they are all gases at a certain temperature, and the temperature part doesn't really matter, but just knowing that it's at a certain temperature, I'll have a certain K. So I'm going to write Kc is equal to my products, and it's a 2C, so that turns into C squared, and use the brackets, meaning concentration, and then divided by my A times B in brackets. And they're all gases, so they should all be in this expression. This is a homogeneous reaction, so this is homogeneous equilibria. It just means it's all in the same phase. We can do a heterogeneous equilibria, and this is where two or more phases are present. It's done the same way, except for you are going to ignore any solids or liquids, because remember, there should be no solids or liquids in your formula, in these expressions. We're going to write the equilibrium constant expression the same way, so Kc. I'm going to look over at my products. The products are both gases, so they're going to go into the equilibrium constant expression. So I have concentration of B squared times the concentration of AC, and then divided by, and I see that A is a solid, so I'm going to ignore it, and then I'm going to have B2 times C. So everything's a gas that's in the formula. So solids and liquids are not put into these equilibrium constant expressions, and that's because their concentrations don't change. For example, if I had water here in this equation, there's no way you can look at a glass of water and make it change concentration, make it become more dense or less dense. It's going to stay the same density, and so therefore it's not going to change in equilibrium when I have dissolved substances into it. If you're asked to calculate the Kp, this is done the exact same way, products divided by reactants, except for you will only have gases and you will put a pressure unit in there. We'll use parentheses instead of concentration, and you write it just as follows. So again, the coefficients become exponents, and I do use these little p's for pressures. On my reactant side, I have C and D, and so I'll do the pressure of C raised to whatever coefficient is in front of C times the pressure of D raised to whatever coefficient is in front of D, and divided by the reactant of the pressures of A and B. Kc and Kp are not the same. This is a formula right here where you can see the relationship between converting between a Kp, which is measuring pressure, and a Kc, which is measuring molarity. But this is not on the AP test. They'll never ask it. So just know they're not the same. And if you have pressures, you use parentheses. And if you have concentrations, you use brackets. Here's another example of heterogeneous equilibrium. Again, my species will be at different phases. This is a reaction where I have a solid that decomposes into another solid and it releases a gas, CO2. And in situation A and situation B, you can see that I start off with different solids, different concentrations of solids. It doesn't matter where you start as far as the concentrations go, but all the solids do need to be present. If one of the solids was not present, then this reaction would not go and we would not achieve the balance. But you see we do end up with the same pressure of CO2 no matter where we start. So in this example here, let's write just a general equilibrium constant expression. So again, Keq is just a general one. It applies to all situations. But products on top don't include the solid that you find on each side of the formula. So here is my formula for that. I just have one product and one reactant, and that is because these solids you do not put into the equilibrium constant expression. If we were looking at gas pressures, that was the value, then instead I would write a Kp, and I'm going to use parentheses. So I'm going to have the pressure of the CO2 and the pressure of my carbon monoxide squared. This one is all gases, so I can put them all in, and it wants a Kc. So again, products, so use brackets, squared, divided by reactants, and these are multiplied. So there's my formula. Write the Kp for this equation. So again, for Kp, you're going to use parentheses. So the pressure of the NO2 squared divided by the pressure of the N2O4. So go ahead and stop the video and see if you can answer these questions. All right, let's get the answers. How do you know a reversible reaction is at equilibrium? You will see the concentrations stay the same. Identify on the graph when the following reactions reach equilibrium. So as soon as they level off, so I'm going to say it's right around 80 seconds for this one. And on this next one, I think it happens more at 60 seconds. So if you think it happened a little bit before or after, it's just a judgment call. But as soon as it levels off, then that's when equilibrium is achieved. And question 3, write an equilibrium constant formula, Kc, for the following. So I have products over reactants, and I see that I have two solids, so I'm just going to put a 1 as a placeholder. And at the bottom, I have A2 squared. So that would be my answer.